Hello everyone. Let's first go over several key concepts. Coordinate system description. Baseline. Baseline azimuth. Tool face. Inclination angle, and inclination compensation value. First, let's look at the coordinate system. The Smart Guidance software adopts the traditional 3-axis coordinate system in the horizontal directional drilling industry, with the entry point as the origin. The 3 axes are as follows. Away, along the horizontal direction, i.e. the drilling direction of the drill bit. Elevation, opposite to the direction of gravity, with the elevation of the entry point set to 0. The upward direction is positive, and the downward direction is negative, perpendicular to the forward direction. Right offset, also an internationally accepted term, referring to the horizontal direction perpendicular to the forward direction. The right direction is positive, and the left direction is negative. The 3 axes are mutually perpendicular, forming a right-handed orthogonal coordinate system. Okay, the second key concept we'll cover is baseline. How is the baseline defined? The projection of the line connecting the entry point and exit point on the horizontal plane is called the baseline. It can be understood as a straight line on the horizontal plane that passes through the horizontal projections of both the entry point and the exit point. From the definition, it's clear that the baseline is a line on the horizontal plane. It passes through the horizontal projections of the entry and exit points, and points from the entry point to the exit point. This direction is crucial because we'll later discuss the concept of baseline azimuth. As you know, without a specified direction, a straight line could have a 180 degrees directional ambiguity, therefore, the direction must be clearly indicated to avoid confusion. In other words, the baseline can be regarded as a ray. It not only passes through 2 points but also has a definite direction. Alright, let's move on to the next key concept, baseline azimuth. The baseline azimuth is the angle between magnetic north and the baseline on the horizontal plane. It indicates the degree to which the baseline deviates from magnetic north, increasing clockwise and decreasing counterclockwise. Magnetic north is 0 degrees, also 360 degrees, similar to how 0 o'clock and 12 o'clock coincide on a clock face. In the absence of interference, the directional angle indicated by the probe can be regarded as the azimuth of that direction. Therefore, if the probe is exactly on the baseline and points from the entry point to the exit point, the azimuth angle displayed by the probe at this time is the actual value of the baseline azimuth. First, we need to clarify a key distinction. The data measured by RTK or GPS is obtained under the true north coordinate system, while the data measured by our tools reflects the Earth's magnetic field. These 2 types of data must not be confused. So how is the baseline azimuth handled in actual construction? In practical engineering projects, there are numerous interference sources around the entry point, such as drilling rigs, drill pipes, and iron fences. Since our probe relies on the geomagnetic guidance principle, the probe cannot accurately measure the baseline azimuth at the construction site. The actual operation is as follows. First, determine the coordinates of the entry point, point 1, and the exit point, point 2, then measure the coordinates of the tail of the rig's power head, point 3, and the coordinates of the rig's vice mouth, point 4. Through RTK coordinate inversion calculation, we obtain the angle difference between the line connecting points 1 and 2, i.e. the baseline, and the line connecting points 3 and 4, which tells us the deviation angle between the baseline direction and the drill bit direction. After starting drilling, maintain this angle unchanged. At this stage, we know that the probe's azimuth data is not very reliable due to interference before the drill exits the construction fence. We should try to keep the drilling direction parallel to the baseline. Once the calculated drilling distance exceeds the fence, approximately the length of 4 drill pipes, each 9.6 meters long, the first beacon measurement is required. Based on the positioning results of the first beacon measurement, we adjust the subsequent drilling direction. The precise baseline azimuth is gradually determined through multiple consecutive beacon measurements. In other words, the baseline azimuth is vague and approximate in the initial stage of drilling. As the number of beacon measurements increases, the baseline azimuth becomes increasingly accurate. Now let's move on to the next key concept, tool face. The tool face refers to the plane formed by the 2 axes of the deflecting drilling tool's bending mechanism. However, when we mention the tool face during construction, it actually refers to an angular value. As shown in the figure, the tool face in construction is the angle formed when the sensor's x-axis rotates clockwise to the deflection bend point. In other words, it represents the position of the deflection bend point on the longitudinal section of the drilling direction axis. This angular value also follows the principle of increasing clockwise, with 0 degrees and 360 degrees coinciding, just like the baseline azimuth. Okay, let's look at the next important concept, inclination angle. The inclination angle is the angle between the axis of the drill pipe or drilling tool and the horizontal plane. An inclination angle of 0 degrees means the drill bit is drilling horizontally. A negative inclination angle indicates downward drilling. Conversely, a positive inclination angle shows upward drilling. This is relatively easy to understand. Unlike azimuth data, this value is not obtained through magnetic measurement principles, so it is not affected by magnetic field interference. Next, let's take a look at the significance and methods of inclination compensation. To understand inclination compensation, we first need to clarify the function of the centralizers. There are two centralizers, positioned closely adjacent to the probe, one in front and the other behind it. Their role is to maintain the coaxiality between the probe and the drill collar, thereby ensuring the accuracy of the measurements taken by the detector inside the probe. However, since the diverter at the forefront of the entire equipment is fixedly connected to the pup joint, the weight of the rear part of the equipment is supported by the centralizers. It can thus be understood that during actual construction, regardless of whether the inclination angle is positive, negative, or 0, the rear half of the entire equipment tilts slightly downward due to gravity. Another reason is that the data displayed by the probe is considered susceptible to interference, while the data measured by the beacon is more accurate. After each beacon positioning, we obtain the relative position of the probe with respect to the beacon. The elevation difference of this relative position in the vertical direction is the elevation data we need to adjust. Based on the number of additional drill pipes used since the last beacon measurement, this elevation difference is allocated among these drill pipes and converted into an angle difference, resulting in an inclination compensation value for each drill pipe on average. By adding this value, we take the position determined by the beacon as the reference and make the probe's position infinitely close to the position provided by the beacon. The above is the significance and specific operation method of the concept of inclination compensation. By understanding the concepts of baseline azimuth and inclination angle, and clarifying the methods and principles of baseline azimuth and inclination compensation, we can have a clear grasp of the navigation construction. Combined with the use of navigation instruments, we can perform direction control operations more accurately and successfully complete the navigation construction.